So, hey everyone, welcome back to another live stream of hacking on the Raspberry Pi Pico emulator. Today we have a very big undertaking. We are going to try to implement the Programmable I, PIO. But before we dive into that, let me first say hey to to Steve and Nekari. Good to see you here in the chat. Let me share my screen. And yeah, so yeah, that's the issues, but I want the open ones. So oh wow, I see Valerio has just opened a new issue just like a minute ago, 7 minutes to be exact. Anyway, before we dive into all the open issues, let's just take a quick look at what we have done since the last live stream. So that was the last live stream, version 050. And we had the working GPIO implementation with this test program that ran successfully. Hooray! And then we went on another live stream 2 days later with a goal to get the MicroPython REPL to work by implementing UART and then just adding a demo program that uses it. And well, it works. That's great. We can now run MicroPython in the emulator. And just to show you, I already added this to Uwokwi. It's still not, there is no public way to get to it, but if you go to uwokwi.com/arduino/news !template MicroPython Pi Pico, it should actually load an environment where you can run the MicroPython interpreter in your browser eventually. Yeah, then if I press play, it will take a few seconds because it has to download the MicroPython, but hey, you get MicroPython REPL and you can do all sort of crazy things there. So I will post the link in the chat in case any of you wants to experiment with that. And we also have it like in the project, so you can just get a MicroPython hex file. I think it's linked in somewhere, maybe in the README, or I don't remember. And then you can just npm run start MicroPython, and within a few seconds you should go and get MicroPython REPL. Yeah, let's try that here. So just for those of you who missed the last spontaneous session. So hello REPL, you know, it works. Amazing. Oops. Yeah. All right. So yeah, what else do we have? So we had this, and then UART RX, and then that's my bad. I committed something I shouldn't have, but it's here, so bummer. I just fixed the Husky. That's the program that automatically runs prettier and ESLint whenever you commit. And people like they committed, and then they had like issues with the code formatting, and that shouldn't happen. So I figured out what happened. If you wonder, is like they released a new version of Husky, and I copied the configuration from a previous project. Long story short, it works now. If you want to check out, there are the details in the commit. And then one of the people who are watching this stream, Proteusnet, I think he said he's from Australia, I'm not sure. Anyway, he added a nice logger, so now we have the ability to define the logging output. So for instance, if we go to this emulator run, actually this one doesn't override a logger, but to MicroPython run, we can see it overrides the logger so that it only displays error messages and not all the messages. So there is like this console logger implementation, and then there is the logger interface, so you can come up with your own logger implementation, and we'll probably do it when we get to tidying up the tests, because some of the tests spit some error messages in the log, so we can just hide them. This is just me improving the time formatting in the log messages. And then Valerio found a bunch of issues with the overflow flag in many of the instructions. So he fixed that. So thank you, Valerio. Thank you so much, Valerio. You also like, let me show you. So you found that a bunch of instructions, like all the adds and sub and CMP, they basically use the same code. So instead of like, this one wasn't treated by, oh, that one doesn't update the flag. So all of those instructions, they basically do the same and update the flags in the same way. So instead of repeating the codes, like the same code like 4 times and then fixing the bug in 4 different places, it just added those 2 useful methods that add 2 numbers and update the flags, or that one subtract 2 numbers. And then I learned that there are words like minuend and subtrahend, if I pronounced that correctly. I didn't even know that was a word. Anyway, so Valerio also did that. This is a quick fix I did just when there is a PKPT instruction, then we rewind the PC in 2 bytes so that the GDB stops on that instruction and not on the next one, just something we missed when we implemented breakpoints. Here I just exported the logging API, so users of the package will be able to use it to define their own loggers. And then finally, this is like what Valerio did with all those instructions that use the add flag and subtract flags that I showed to you. And finally, I fixed a quick error here. It didn't use the logger correctly. I mean, it used like an older implementation before we refactored. Never mind. Anyway, so that's just related to this new logging API. So to summarize, we got MicroPython, we have now a logging API, and we have a bunch of fixes in the flags. And now let's take a look at the issues. So first of all, there is this issue, and it's an interesting one. This was found by Steve. He was playing around with MicroPython, and then he found that some piece of code with recursion didn't work. It printed an error about local variable, missing local variable, or something like that. And then we figured out by the error message that was showing when he was trying to run his code example. Oh, here it is. There you go. So it says like local variable referenced before assignment. So it also printed this error message about accessing writing to invalid memory location. And by looking at a stack trace, we figured out that the str instruction, there is this problem where if you use 2 registers, one of them is like a negative value, then the value goes over 32 bits and we don't round it in the str instruction implementation. Let me show that to you. So that was str. Yep. So so we this one str register. So we just add 2 registers, then we update the number of cycles, and then we use that address without rounding it. So if we just why isn't it happy? Oh, that's, I don't know, it always messes up with this. Anyways, so if we copy the test case from this issue, then where is the instruction spec? str. Yep. So let's add it after all str. So it will obviously fail now because this is the bug. And if we take a look, if we focus on this and then go to the str, so you can see this here, like console log address to string 16. You can see that the resulting address is like too big for 32 bits. So that's like a very big number. It should have been this, but there is also this one. So there are like a few ways to fix this. I mean, we could obviously do something like just, truncated at 32 bits, and I'm making this unsigned because some of the addresses they go above 80 million, like the SAO. So we have like all those SAO addresses that go above the negative point, and or all these addresses inside PPB base, and we are just comparing numbers, so it needs to be unsigned. So that's one way to fix it, but the thing is, I suspect there is like the same problem in all of the other STR instructions, like strb register. We are doing the same calculation here and also here. And then there is like those LDR register that also do this calculation and can be affected by the same bug. So I think the best way to fix this would actually be to make sure that those functions, slow IO and all those read functions, will just truncate the address to 32 bits. So like header, we can say it's just truncated to our trick to unsigned, convert it to unsigned 32 bits, and then let's also do inload uint 32, read uint 32. Yep. So we can also do it like here, it's called address, and then oh boy, what happened here? And then actually here there is no problem, because this will definitely convert the address to 32 bits, but it will be signed. So this might solve another bug. So reading from SAO 16 bits or 8 bits would probably have failed. Anyway, let's do the same with the write. So now this should be green, because yeah, we fixed this this issue. And let's see, for the write uint 8, yeah, I think that should also work, because oh, here we go. That could be a problem. Find peripheral. I mean, this is all like yeah, I guess we should probably convert this one to unsigned as well, just to be on the safe side. So probably the same here. And let's see, and then where else do we use address? So inside find peripheral, and then this one already takes the aligned address, so no need to worry about it. So just inside find peripheral, let's also make sure that the address is always okay. That if we are shifting it, then that's going to to fix that, to make it 32 bits. So okay, so that should probably fix the bug. I mean, the test now passes, so let's just commit this as a blitz bug fix. Yeah, fix RP2040, and yeah, negative offset, maybe negative offsets. Or no, let's keep it that way. Close 43. So this is like the test case that we added based on the issue, and this is like the solution, just fixing even more. This should fix all LDR STR variants, as well as any usage of write read uint 32 and write uint 32. So if in the future we have some peripheral, or I don't know, whatever calls those functions, now they will be resilient against like big numbers. They will always truncate them to 32 bits. Or so I hope. Anyway, let's commit that, and we'll push. That was a quick warm-up, committing, fixing this issue. Commit, push, remove this file, remove this side pane. This one should now be closed, and or maybe I didn't. Yeah, close this. Yeah, now it's closed. That was that took it took GitHub like a second to update. Anyway, so there is like also this like 2 Pico SDK tests, and Graham said it would be nice to have them passing, so we could use the emulator to test is for the regression tests for the Pico SDK. They still don't pass. We'll probably take a look at that in the future, maybe in another spontaneous live stream. And there is this new issue from Valerio, and Valerio has been really good at spawning those issues and fixing them. So if you are up to it, Valerio, I would love to see how you fix this. And it's like running GDB diff like crazy and fixing bugs, which is amazing, finding all those like small bugs. But today, let's go for the main dish, the Programmable IO, the PIO. See chapter 3 of the RP22 datasheet. That's all that the is that the correct one? No, I'm looking at the wrong datasheet. That's all that the issue says. So let's take a look at that. So PIO, yeah. Our best friend, the datasheet. No, not the USB. What happened? Yeah. So there are 2 identical PIO blocks. Each block is blah, 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 blah. And yeah, so I spent like the last week digging through this datasheet. So I will have a pretty good understanding of how it works. In a nutshell, there is like 4 state machines for each PIO. And then they have like 32 instruction memory. So there is like 32 slots that the user can fill with instructions. And then all those machines read from the 4 machines read from the same slots, but they can like execute different code sections from those slots from this instruction memory. And then there are like there is like 2 internal registers, and some ways there is like a way for the program running on the Pi Pico to send data to the PIO machine and to get data from the PIO machine. There is like those registers, shift registers in and out. So this is like the program is sending data to the PIO state machine, like the Pi Pico program to PIO, and then PIO to the Pi Pico program, and 2 like local X and Y registers, and then there is like PC, which just points to the current instruction, and there is a lot more. And it only has like 9, I think. 1, 2, 3, 4, 5, 6, 7, 9, 10. 2. Yeah, it's 9. I just don't know how to count. Anyway, there are like 9 instructions that control this state machine. So we need to implement just 9 instructions, and they get like a bunch of parameters. And I think one of the challenges would be to write the test code for this, like to find a way to test the state machines that also works against the physical hardware. But I think I have an idea how to do this. Let me show you. So these are like the registers for the PIOs, and these are like the FIFO. So when you write to this register, it sends data to the state machine, and then when you read from this register, it can read data from the state machine. So that's how the program interacts with the state machine. And then there is a bunch of registers for all the instructions. So this is how we can like upload the program into the state machine. And then for each state machine, there is like a bunch of registers, and one of them, this one, you can write to execute an instruction immediately, including jumps, and then resume execution. So basically this one would allow us to, just push a single instruction and execute it immediately. And I think that's going to be super useful for debugging. And then there is like those registers that let you read to sample the PED output values. PIO is currently driving to the GPIO, so that's a way to get data from any instruction that modifies the pin, controls the pins or the pin or the output enable of those pins. So I think those are going to be very useful in debugging. Anyway, Hey Tomasz, good to see you here as well. Anyway, before or not before, we are going to jump in, right in. Let's do this. Yeah, as usual, I have no idea what I'm doing, but that's the way it works. Why isn't it happy here? Or something is, I think for some reason, yeah, it doesn't find the types for Node.js, but I think we do have this Node.js types. Probably, I think what happens is whenever, yeah, that fixed it. Whenever I publish a version, it deletes the node modules directory with all the types, and then this causes this causes Visual Studio Code to lose the type information, and then like it reports errors in some of the files. Now this error here is also gone. We had like this error about the timer, this one, and it's gone. Cool. Anyway, so let's create PIO.ts and export class RP2040, and that would just be a peripheral. We can probably copy one of the other peripheral. That would be faster. So RP2040, and yeah, we don't need all of that for now. So I don't know if we need a constructor. We'll probably need some custom configuration per PIO. Not sure if we do, but let's keep it for now. And then let's remove this and just keep this scaffold of readyUint with default return and writeUint with the default return. Default write, not return. Okay, cool. So we have this, and then let's go to RP2040 and let's implement the PIO. Let's plug it in. Wait a second, where does it go? I don't see it here. Oh yeah, that's like in the different bus. It's not like the standard peripheral bus. So let's do it like that. Read only. Yeah, read only PIO. It's amazing that every single thing like has its own. It's another spatial case or something like that. RP2040. And that's this, and PIO 0, and then there is also PIO 1, and then thinking, yeah, we should probably not use the peripherals for that, because then we'll have like those atomic writes which do not happen for those like peripherals. Where's this? Yeah, it's like PIO is like AHB light peripheral, and it's not like all the other APB peripherals. So that's different bus. They probably behave differently. Yeah, it's together with the USB and the DMA. So I think we have some code to deal with the USB. Yeah, probably that one deals with the USB. So let's do for now. We'll probably need to refactor this to be a bit more user-friendly, but let's have, this is like PIO 0 base, PIO 0 base, and PIO 1 base is just this, right? Yes. And then if we are writing there, so SIO PIO base, oh no, just PIO 0 base. So this just goes this.PIO 0, write uint32, and that's address minus this and the value. Otherwise, if it's just like write uint32, and we also need to implement read uint32. So for reading from this, yeah, let's have, so if it's like, oh, we also need to take care of PIO1. We'll do it in a moment. So redo int, but let's first of all finish this. So probably this one should just say 1, and then PIO1. And where is like that one with the right? Yeah. Now let's repeat this one for PIO1 as well. Okay, so finally, I mean, not finally, we finished plugging it in int 34, just to make sure I didn't make any mistakes. So yeah, 0, 1, 0, 1, seems good. So now we are able to read and write from PIO. And now let's start like working on the actual PIO implementation. And that's not a peripheral per se, but let's keep them extending base peripheral. I mean, all those, this is not useful here, but the other behaviors are useful. So let's try to keep that for now. And the first thing I want to do, I just want to go over the registers and have constants for as many as we can. I don't know if it will be easy to copy this. Yeah, that's going to take a long time. And there are like so many repetitions. So yeah, let's yeah, I guess we would at least need those. I mean, these are like they repeat for all the machines. They are not machine specific. Control. Yeah. Const. Cool. So we have those, and these ones are machine specific. So we'll deal with them in the machines. And RQ isn't machine specific, as well as RQ force. That's not machine specific as well. Okay, and then I guess this is also not machine specific, and yeah. And all those debug registers. We don't need this, we don't need that. Okay, these are like all the instruction memory. So we just need the first one and the last one, and then we can just have some sort of array. So this one is 48, and the last one is 31, like the last slot. So 31 is C4. And then there is like those state machine specific registers, so they repeat. And then we also have like those interrupt and IRQ registers that I think are shared. And that's it. That's, oh yeah, that's all the registers that we need. So yeah, let's do those. And oh, yeah, this way. We can probably keep the comments. They are not useless. Okay, so yeah, we have those, and I think we also need to yeah, let's do it like having those registers just for one state machine, and then we'll like use them in the others. So these are like generic registers and state machine specific registers. Cool, let's do them. Const yeah, just keep the gist of it. And pin control is just like state machine pin control, not very useful. Anyway, so we have like those, and then we had also like those FIFOs. So yeah, so yeah, there are like the FIFOs that are machine specific. So const txf0. Yeah, I mean, maybe for them we'll just have them in the big switch, because I don't think it will be it will save us a lot of code if we just, you know, have a different handling for those. So 14, 18, and txf3 is 1c, right? And then rx is like the same with the 20 in the beginning. So x and 20. Okay, so we got sort of all the registers, and now let's also implement a state machine class. So we'll have 4 state machines. So export class state machine, and it will probably have yeah, no, we don't know. It will probably need access to the RP2040, and probably also need access to the PIO. Yeah, those can be read-only and maybe also private. Yeah, here we can also make them read-only. I mean, we don't need to, because the super does that. Okay. And then for each state machine, we are going to have some state. So I think the first state, we know they're like those registers. So registers, I think there are X and Y. And there are also a few more registers which we will implement in a moment. Let's set them to start with 0. I'm not sure how they are initialized, but we can probably check it out later. And we also need like an array to store all those instructions. So let's just have this, and the instructions are shared. So it could be uint32 array with 32 entries. So new read only, and yeah, so let's do this super switch. So switch offset, and then according to the offset we can read only machines is just the array of 4 state machine. So this.rp2040 with this.pio, or just this. Yeah, maybe we should also like add an index, so if we need to debug it at some point, it will be easier to do it. So this is just sequence starting from 0. Yes. Okay, so yeah, now we have like an array with 4 machines, and then based on the offset we are going to do stuff. For instance, let's just take all of those like reading. I guess these are like RX or read only, those FIFO. Read direct read, yeah, it's RF read from FIFO probably. One word from the FIFO attempting to read an empty FIFO. So we also need a FIFO for the machine. Yeah, we'll implement it in a moment, but let's just, you know, create a switch cases. So case this, case this, return these dot machines at the same index, read FIFO, and we'll add this method in a moment. And then let's also do this the same for writing. So here it's just going to be tx, and then instead of return we are just going to write FIFO with the value and break. So now we have like this redirection, And let's add those methods, read FIFO and write FIFO. And luckily, we already have a FIFO implementation because we created it in the last spontaneous stream for the UART RX. So we can, let's make those private, or maybe not, so we can debug them. Read only RX FIFO is just a new FIFO. And I think that the size of the FIFO is 4, if I remember correctly, but let's just make sure this FIFO control flow, PIO programs. And that's not, what is RF? Yeah, okay. Where is the FIFO definition? Somewhere here. TX FIFO, but does it say how large the FIFO is? I think it's 4 entries, if I'm not mistaken. Yeah, a lot of text. Yeah, maybe stalling. Nope. Maybe push and pull, they like affect the FIFO, so maybe they have some information about the size of the FIFO. Single, nope. Yeah. What is that? FIFO joining. Oh, finally, each state specific possesses 4 entry FIFO in each direction. Cool. And you can join them into a single FIFO. Okay, but for now, let's not worry about that. Let's just create 2 FIFOs, so TX FIFO and RX FIFO. And then let's see, reading from those FIFO registers, what does it do? So obviously, I mean, it's obvious what it does where the, yeah. So yeah, if it's empty, then the data is undefined, but we also need to set this bit. So let's do this. So if this.rx FIFO.empty, then we just return 0, which is sort of undefined, and we also to do set this bit. Otherwise, we just return this.rx FIFO.pull. Gets an item from the FIFO, cool. And I guess the same goes for writing to FIFO. So full has no effect, but it says this bit for the FIFO. So we need to, if this tx FIFO.full, then to do set. Okay, otherwise we are, yeah, if it's not full, then we are going to push. Otherwise, this.tx FIFO.push value. Cool. So yeah, we have the one side of the FIFOs, which is controlled by the program, and yeah, and now let's take a quick look at this F level register to see how it works. So where is that list of registers? F level. Yeah, we have like oh no, the fdebug. So yeah, we have like 4 bits for yeah, let's implement this as well. So yeah, we can probably have this flag right on this RP-PIO. So fdebug, which is probably all zeros at the beginning. Yeah, and this is write clear. So we need to take care of that as well. So if somebody is reading case fdebug, then return this.fdebug, and if somebody is writing it, then this.fdebug, it's write clear, so we need just to, and then break, clear the bits that the user has to set. And then here we can just do something like that, txstall, and here the index of the FIFO is already useful for us. So let's add fdebug bits. So we have txstall is 1 shifted by 24. Yeah, and there is tx over, which is by 16. Probably same for rx, I guess. So rx under is shifted by 8, and rx stall, right, is just the first bit, first 4 bits, rx stall. So just the first 4 bits, and now we can do this to do this.pio.fdebug or equals. So we need to just take txstall, right? Oh, tx over, sorry. Maybe we can call it like this, fdebug underscore, like in the datasheet. So fdebug tx over, and then we also need to like shift it by this the index of the current state machine, so it sets the correct bit, and same goes here for rx under, and return 0. Right, I think we are good with this FIFO and half of the fdebug register. If we are in these registers, let's also like implement those other registers. So there's like read-only fstat. Yeah, interesting. Oh, this is like for each of the FIFOs. So let's have this fstat as well. Let's implement it, case fstat. So return this dot. Yeah, we need to check for each of those, all of those bits. So let's define those bits for a moment. So we have fstat bits. And yeah, it's probably in the same jumps as before, 0, 8, 16, 24. So we can probably copy this and just change their names, fstat. And then this is like dx empty and dx full, rx empty and rx full, and rx full. Okay, and now we can just figure out the state. So yeah, we want to return this dot machines 0.txFIFO.full. So if it's full, we want to where is that? That was fstat tx full. Or maybe we can have like fstat per machine, so just not to repeat the same code 4 times. So we can just do 0, 1, 2, and 3. Then we need to implement this fstat getter, so we can do get fstat FIFO stats, or maybe we can give it a better name, FIFO stat. Okay, and then for that we would just need to implement those 4. So return, so if this.txFIFO.empty, then this, otherwise 0. Okay, or if this.txFIFO.full, then txFull, otherwise 0, or this.txFIFO or rxFIFO.empty, then rxEmpty, otherwise 0, and finally if this.rxFIFO.full, then f.rxFull, otherwise 0, and yeah, I think this will compile once I figure out yeah, okay. And now we need to do one more thing with this. So this is the correct bit numbers for empty empty, full full, rx 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 rx. Yeah. This is like the correct only correct for the first state machine, but if it's like a different state machine, then we also need to shift them by this dot index, so by the state machine index. So this looks, maybe we'll do it in 2 steps. Const result, and then we just shift the result by, I think this is a bit more readable. So yeah, we calculate the bits for this state machine and then shift them by the index of the state machine to get a correct bit set. And hi Puneet, good to see you here in the chat. Okay, so hopefully we also got this fstat register implemented. Let's see what if we have anything else for the FIFOs. I think there is like f levels, so it just returns I guess there is probably, this is like read only, right? It's probably returning the number of items in each FIFO, because this is like 4 bits per FIFO. So yeah, let's also just implement that. Don't know if it will be useful for debugging, but we are there, so why not? Case f level, and then we want to return. So basically tx0 this dot machines 0.txFIFO. I think there is like machines 0 txFIFO dot item count. Yeah, that sounds like the right one, and it has to be I mean it should never be more than like 4 bits, but no, just for the sake of it. And then we also do the same for the rxFIFO, so rxFIFO. But this time we are also going to shift it left by 4, because that's the 4 next bits. And then we are going to repeat it for like txrx, txrx, txrx. So txrx, and this is like machine 1, and now 8, 12, and machine 2, and machine 3. And here we have 16, 20, 24, and 28. And hopefully I didn't mess up anything and it will just work. Yeah, this horror of bitwise operations. And okay, so at this point we already have like all those registers, they are covered. This is pretty nice progress. I think the next thing we are going to do is the instruction memory registers. And this is like easy because it's just write only, so we don't have to worry about reading from those. Just yeah, I think we can add like a spatial if, so into the write uint32. So if offset is more than this, offset is less than the last instruction, then const index is just offset minus instruction 0, and it's like the jumps are like it jumps by 4 bytes per entry. Oh, where did it go? Yeah, so it jumps by 4 bytes per instruction, as you can see. So we just need to divide it by 4 or shift it right by 2, whatever works for you. and then return, and then this dot instructions at index equals value, and we are just taking the lower 16 bits because those are only 16-bit registers. These bits are not used, which is a shame, I guess, because they could have been used for adding more instructions, maybe. I don't know. There must be a reason they chose 32 instructions for the PIO. Actually, Graham, if you are watching it and you know the reason, I would love to learn why. Cool. So at this point, we have like those state machines. We can write instructions, and we still need a way to execute them. And for that, we are going to implement all those registers that are interacting with a specific state machine. So starting from this CLK until this pinctrl, all those like 1, 2, 3, 4, 5, 6. So let's have another if offset is more than SM0 CLK offset is less than what's the last one? That would be SM3 pin control. SM3 pin control. I think we'll need to define this one. Then this dot machines dot this dot machines dot write register, or maybe write uint 32, and then we need to so we need to figure out machine index. It's just like I guess what's the difference between two machines registers. So this is like D0 and E0. So just 10 hexa, right? Or wait a second, no. C8, CC, no, it's more than 10 hexa. Doesn't play nicely. So I guess we can probably do it like that. Not the best way, but it will work. So just have the extremes for like one condition per machine. There must be a better way, but if you find one, then send a pull request later. Okay, so if this is it, then this dot machines dot write register, and then I want to write uint 32 offset value just for this to the machine, so we don't need machine index. And then same goes for 1, not SM0, SM. So this is 1, and this is machine 1, and then we have here like 2 and 3, and then we'll have the same inside read. So if we have all of those offsets, then we just return instead of. So that would be calling to read uint 32. And maybe to make our life a bit easier, then we can sort of make sure that they always like get the we can all just, you know, subtract this and subtract this, and so they get relative offset, so they don't have to worry about which state machine they are. They always get like this relative offset, not from the value. SM0 pin control. Okay, almost. Autocomplete doesn't quite work well. Okay, and now we also need to implement like, oh no, I didn't want to subtract the pin control. I wanted to subtract the, I wanted to subtract the clock div, the first one, CLK div. And then the same goes for read, I guess, readUint. Yeah, same here. So CLK div, and here as well, CLK div. And let's also define all these missing ones. So we have like pin control. So this one is at F4 count. This one is at here, and this one is here. Okay, and then we also need the other one, like the first one that was a CLK div, I think. Yeah. So all of these. And this one, and then let's just make them const equals, then we have those values to sort of split amongst them. And this one, yeah, it looks fine. Just remove these extra commas, and I think we are good. So we have this mechanism that redirects all those registers into the respective state machines. So the next thing we need to do is just write uint32 and read uint32, and just this one gets an offset, and this offset is like relative to the beginning. So we can just do something like that, just to make it just add the SM0 CLK div, so we can use those registers. So then let's take a look at those registers. I think I guess some of them are read-write, some of them are probably read-only, as we are used to, but let's first of all add a switch, and then let's see, so it's offset number, and this one also get the value. Hey Valerio, great to see you here. So we are working in the middle of working on the PIO. I think this is just setting up everything, all the registers, and then once we are more or less done with that, we'll do the execution logic, which is probably going to be a bit challenging. And at least I want to at least write one test, end-to-end test today. Maybe we will not implement everything, but we'll at least have the test in place. Okay, cool. So we have those registers. Let's see what they do. So this one is just the clock divider, and it's basically read-write. So let's split it like they do into clock div int, and that's 1 by default, and clock div frac, which is 0 by default. And then when reading from it, we can just case this, just return this dot clock div int, and this is like the top 16 bits, so shifted by 16, and then there is like this dot clock div frac shifted by, I guess, 8, yeah, and then 8 bits are useless. And then let's do also the opposite case, SM0 clock div. So if writing to this dot clock div int is just value shifted by 16, and this dot clock div frac is value shifted by 8, and we are just taking 8 bits. We can do it. Doesn't really matter, right? We can do this kind of shift, so it's uniform. Okay, so we have this ready, and now executeInstruction. Whew, this one has a lot of flex. And yeah, everything is read-write except for exec stalled. Okay, so we'll have all those flags in a moment. Let's see, what are those? Shift-ctrl. It also have a bunch of read-write stuff. We'll get to that. That's where the actual work is. This one is easy, just return the current instruction address. So we'll have like PC program counter, and then we can just for this register, what was that? Maybe we should, why is that not happy? We'll get to it in a moment, but yeah. So we said this one is read only, so we don't need to write to it, but let's also mention it read only, so you know, we'll know we took care of it. And then here we are just returning this.pc, and let's take a note of those two which we still need to implement, those extra complicated case return this dot. Actually, we can just have a register that will, for now, will take care of that. So then we can see what we are doing with those bit, this.executeInstruction, and for that one we need to take care not to write to this biggest largest bit, so need to implement it in a way that this bit is always copied. So we can take value and all of those yeah, and then we can this.executeInstruction and the highest bit, missing a 0, and let's just always make sure this is unsigned. I think it doesn't really matter if it's signed or unsigned, but you know, just to be on the safe side, we have been bitten by that multiple times, and I think everything here is initialized to 0, right? No, we have this like 1F here at bit 12, so 1F shifted by 12, right? 12, yes. Well, this is the initial value of this register, and then we have that shift-ctrl. We hope it's also like it's not like, also we don't need this number if we are initializing it. Yeah, I hope it's all initialized 0. No, it's not. At least it's all read-write. So this has like bits 18 and 19 set to 1, so 1 shifted by 18, and then let's implement the getters and the setters. Case SM0 shift control, return this.shift control. At least when writing it's going to be simple, shift control. This.shift control equals to value and break. Oh, nice. Valerio said he sent us PIO assembly implementation. We'll have a look at that. That could save some time. Thanks, Valerio. We'll probably get to that in a moment. So once we finish with the register. So there is like address, which we implemented. We just did this shift control, right? And now there are like, I think 2 more. So instruction, and read to see the current instruction. That should be quite easy. So reading from instruction case should return this dot PIO.instructions at this.pc, just returning the current instruction. And when writing, we need to execute an instruction immediately and then resume execution. So when writing to this case SM0 instr, this dot execute instruction and then value. So we are executing. We only need the lower bits of value. Break, and we'll create this placeholder for execute instruction and then opcode number. Okay, and then we have this finally this pin control, right? And then we are done with those registers. Cool. So we have like everything is RW and most of them are initialized to 0. So let's create the variable. Pin control is everything is 0 except from 5. This is initialized to 5 and set count that's shifted by 26. Okay, and then case SM0 pin control, return this dot pin control, and then here case SM0 pin control, this dot pin control equals value break. Let's see again, everything is read right. Okay, cool. So yeah, so we have like yeah, and we need to implement this. And why is this not happy? This returning undefined. Yeah. Otherwise we just return 0. There shouldn't be any otherwise, so let's this dot PIO.warn read from invalid state machine register. That's the new logging framework from Proteusnet. Thank you for that. And let's also like add here default write to. Actually, it's not a warning, it's an error. It should never happen. So we want to know if this happened. Cool. So we took care of that, and then what? Oh, we need to implement that. To implement me. Okay, but there we go. We have the beginning. 256 lines of code just to handle most of the registers. We still haven't done the interrupts, which we'll do, and all those RQ and debug registers, which we'll probably do, and control. What is this control register? Probably useful. List of registers, control. So it allows us to restart the state machine and disable them. Okay. SC, this is, what is SC? Probably it means that it's write only because you can't read from them as far as I can see, and it just does something when you write to it. So let's have also like an enabled bit for each machine, Boolean, and by default they are all disabled, so it's enabled is false. And then let's implement this control register. So this is like reading. So in case we are reading, we are just returning this. Yeah. If this enabled, then 1 shifted by 0, otherwise 0. And then we can just copy it 3 times. And yeah. And then insert a sequential number starting from, no, that didn't work as I expected it. Let's just do it manually. 2, 3, then 1, 2, 3, and true. That's ugly. Let's add some parentheses to make it a bit more friendly. Okay, that's better. So yeah. So first of all, cool. And then let's implement writing to this register. So writing to control. So yeah, we can just write yeah, it's read write. So basically you can value and 1 0 then true, otherwise false, and repeat this 3 times. And here again as well. Okay, and now we also need to sort of implement those restarts, which clears the input, the content, the delay counter. Okay, we'll just have a, so these are like bits 4 to 7. So if value and 1 by 4, then this machine's 0.restart. Maybe we can, yeah, we can probably do this in a for loop. Let index less than 4, index plus plus. So 0. Oh, yeah. So basically, just index and then, or maybe index. We can just keep it index, and then if value and 1 4 plus index, then machine at index.restart, and we'll implement that soon. And then we also have like a clock div restart, which I don't know if we need to implement it, but let's just make sure that we have what's needed. So clock div restart, and then we can do the restart and clock div restart methods. So restart and clock div, and for now we'll just for clock div we'll just throw a warning, this dot PIO dot warn clock div restart not implemented. Okay, and for restart, let's just see what it says. Yeah. So input and out shift counters, input shift register, delay counter. Whew, a lot of stuff is cleared. Any stalled, any pin right. Okay, so to do, we don't have those yet. Yeah, we don't have. I wonder what's the difference between the input shift counter, input shift counter, and the content of the input shift register. Okay. We'll probably need to implement them in a moment, but at least we can say, oh, we swapped them. Yeah, so restart isn't implemented yet, but at least we have some to-dos, and the same goes for clock div restart. And voila, we have we don't have to worry about this control register anymore. So yeah, in terms of registers, we have covered most of them except for those IRQ, input sync, and those debugs, which we'll probably get to in a moment because we'll need them well for the tests. And then yeah, I think at this point we want to do execute instruction, which is like the core of this. But let's first take a look at what Valerio just did. Yeah, he said he sent a pull request. I don't see, oh, it's under pull request, of course. So he implemented, maybe useful for test creation. Let's see what's that. So he has like PIO Assembler, which has a bunch of useful, I guess, constants, and then like probably implemented all the opcodes of the PIO. There aren't too many, but yeah. Yeah. So yeah, so first of all, Valerio, thank you so much for implementing it. A few notes, I will merge it and then we'll fix it, but there are like a few things that already jumping into my eyes. First of all, like the name of the variables, they should always start with lowercase letter. That's the convention. Also, I don't think TypeScript would allow you to set a default value for one variable, for one parameter, but not for the one that follows it. So if you say give this one a default value, then all the following parameters should also have a default value. Yeah, and I think other than that, it's pretty great. Oh, and we also need obviously to export all of those constant as well, so people who are using this assembler will be able to use them. So yeah, usually I would just write a bunch of comments. That's what we usually do, and then merge them. But for now, you know, I'm going to just merge them as they are. Squash and merge, fit PIO. PIO some implementation, great, thank you. And let's just pull rebase, so we get this new, oh, it doesn't like that. I guess we can pull, I hope that's, oh, we haven't committed, so it's not going to create a merge commit, which is great. And yeah, we now got this like new PIO Assembler. Yeah, so let's quickly fix the issues that I mentioned. First of all, let's export all of these. So they are going to be exported here, so users can actually use them. So they don't have to repeat this. And again, Valerio, thank you for the PR. And thank you for letting me know in the chat, otherwise I would have just skipped that. And let's fix the variable name, so cond address and delay, and pol is probably polarity, src index and delay. And these are just like utility functions to encode. This one is fine, delay. And this is, I don't know how TypeScript allows this. It shouldn't let you set interesting a default value if you didn't set it. Great. I didn't know that was possible. I thought that was an error in TypeScript. Anyway, let's fix this one. Delay. Again, delay. So what I was thinking, there is like a command line tool that does this for us. So I was just thinking to use it, but I think this would be better for the test. So the SDK test data and delay, right? And let's see how they are. Now we need to fix the test because yeah, we need to import all of those. Yeah, okay. Tests are happy, green. Yeah. Maybe I would just, instead of Ocode PIO, I would just change all of those to be just PIO. I think it's pretty clear. It's only going to be used in the tests, and in the context of the test, it's probably clear that this is like an PIO opcode. I think it's a bit more readable without having this uppercase PIO in front of each of the instructions. Cool. So yeah, I think that's push if full no block. Yeah. What is this 12? Not sure. It's probably no block. Is there like a constant for that? Block. No. Okay. Oh, that's probably need to go lowercase. So yeah. So maybe I think and We can probably tidy it up later, but I think we can probably, for some of those, turn them into booleans instead of numbers, because they are just booleans. But yeah, let's not worry about it too much for now. It's just test utilities. Yeah, let's hope this works. Just looking at this test X invert status, yeah, it looks pretty nice. I mean, I don't know if the encodings are good. I hope they are. I trust Valerio here, but at least the test description seems to match what the test is testing. Okay, so feed PIO, tidy up the PIO assembler, and let's commit that as well. And now we can start, I guess, working on implementing this instruction set. So do the opposite of those tests. Let's push it. And yeah, we have execute instruction, and it takes an opcode, and then it needs, first of all, to decode this opcode. So if we take a look at the datasheet, there are like, thanks Valerio, I will close this for now. There are like those opcodes, and we can check those bits to figure out which opcode we are interested in. So these are like the high 3 bits. So we can probably or we can just switch opcode shifted by, so those are bits 13, so we need to shift by 13, and then case 0, then JMP like, and maybe we'll have case 1, maybe we'll have one function per instruction. Don't know yet, we'll figure it out in a moment. Wait, then we have in, then we have out, then so out is 11, and then we have I think push and pull, yeah, they have the same prefix, so that's push or pull. And then we have move 101. That's how you encode 9 instructions with only 3 bits. You give you use the same encoding for 2 instructions. And then there is like IRQ is 110, and I think the last one was set. Yep. Okay, so yeah, we have the initial decoding, and then yeah, I think the thing is we have like a bunch of there is also like this delay side set, so we can probably decode it here. Const delay or side set is just opcode shifted by 8, and then bitwise end with 1, 2, 3, 4, 5, so 5 bits. And then we also have like arg, which is per instruction, which is like the lowest 8-bit. Cool. So yeah, let's start looking at the instructions and implementing it down. First of all, let's see what tells push from pull. So I think it's this bit is the difference. So we can oh, I see those bits must be 0. So yeah, if arg, then this is pull, otherwise push, and this is all true only if, I think the other ones, yeah, this is, oh, this one also has this bit need to be 0, so let's add it as well. If if then return unknown instruction, that's not valid, it has to be 0 here. So if it's set, and here if arg, yeah, we can probably return instead of break instead of return, just to be consistent with the rest. And here if arg and all those like 5 bits, if they are not 0, then break as well. That's unknown instruction, it's not a valid one. Okay, and now if it's set and this is pull, otherwise this is push. Okay, so now we know how to decode the instructions, and we can start looking into the implementations. First of all, let's, yeah, I think this works better. This looks better this way. In and then out, and then that reminds me a bit of like the ARM instruction set implementation, but I hope this is going to be faster and sweeter. And finally there is like set. Okay, and then let's take a look at the instruction details. So we have jump, and jump has a condition and address. So set a program counter to address if condition is true, otherwise no operation. Delay cycles on jump always take effect whether condition is true or false, and they take place after a condition is evaluated. So let's do that. So we need to do if condition, and we'll do that in a moment. Then this.pc, they're taken place after. So first of all, we need to update the PC to erg, and we need to take the lower 5 bits, that the address. And then let's take a look at the condition. Const condition is yeah, we need to shift it by 5 to take just those bits, and then depending on this value we need to decide whether we take the branch or not. So yeah, maybe we'll have another function for that. So if jump condition that takes this condition and returns true or false. So jump condition boolean number, but it can only be from one of those. And then let's just switch condition, then depending of and the condition, yeah, so we can probably turn all of those into cases. Case this, then let's just add a comment so we know which one is which. So this is always, so this is true, and this is if this.x is 0, right? Oh, we also need to add a binary prefix for them to them. And then all right, so this one is a bit complex because it always also, oh, actually we can, don't really like this, but we can, yeah, we can use post decrement in JavaScript like this one. Return this dot, oh, we need to be careful about that because we need to make sure that the result is still, yeah, we'll probably fix it in a second. But this is where did the comment go? We had a comment. Why did I delete it? So this is if y is 0, and this is actually, so we can do something like this. Yeah, I think, does it always decrement x? I guess it does, even if it's 0, but we'll have to verify that. So if, yeah, well, we'll do it in a moment. We'll fix it in a moment. Same goes for this. To do me and do this, and then let's see. So this is a bit simple. Return this dot this.x doesn't equal this.y if they are different. Branch on input pin, we need to do it, and output shift register.empty, we also need to do it. So for now we'll return false, and we'll get back to it in a moment once we add this register. Okay, so yeah, for those post decrement, so if this.x, or let's do it like that, old x, this.x, we can probably do it at the beginning, so, or no, let's do it here. Yeah, we just need to open a block if we declare a variable. That's a thing in JavaScript. In TypeScript, it doesn't like it otherwise. This doesn't need to change, and then this.x is this.x -1, but we need to make sure it's 32 bits, and then return old x is not 0, and same for y post decrement. Just everywhere where we have x, it should be y, and here as well. Okay, and then we only need to do those branches, but other than that, we have done this jump condition. We have finished doing jump. Great. So we have those to-dos. We'll come back to them sometime. Let's take a look at wait. So yeah, wait is waiting for something. So I guess yeah, so yeah, we have to check until some GPIO is changed, or until one of the input pins applied by the state machine, or until there is an IRQ. Okay, and then we probably need a way to sort of listen for that and wake the machine up. So maybe we need to have some variable that will tell us what we are waiting for. But for now on, let's keep going. Let's see what in and out does. So in reads bits from source into the input shift register. So there is like input shift register and input shift count. Let's have them. Input shift reg equals 0, input shift count equals 0, and then in should just stuff something in. So it can read from a bunch of places. ISR, I think, is input shift register. Interesting. So it can read from the input shift register and push it into the input shift register. Okay, I don't understand. Yeah, ISR is, I'm not sure, but why? But it's possible. Yeah, maybe it says something here. What is now? All zeros. No, I don't see something that says what shifting in from ISR to ISR. Yeah, so yeah, let's, oh, there is also shift direction. So it can be shift to the right or shift to the left. Let's take a look at that shift there. Shift there. It's out shift there in this shift control. So first of all, let's define this register, this bit. So that's shift control bits, and then const shift control out shift there is just 1 shifted by 19. So this is the thing that controls this. Okay, and now we can sort of implement this. So just take add this description so we remember what it means. Shift right, 0 to the left. Okay. So now inside the in instruction, we can sort of read this value to shift and then shift. So yeah, let's go back to the definition of in. So we have like bit count and source. So yeah, I guess well, const bit count is just the lowest 5 bits. Right, and then there is source, so const source value, and let's have this dot in source that takes those bits and returns the or in source value that does this calculation for us. So it takes I would call it source number and then switch source and just copy this table. Yeah, and we still don't have pins, but pins are basically like the input pins, I guess. So we'll need to do it in a moment because I think we already have them. Oh, branch on input bit, that's different. Yeah, anyway, we don't need that. Keys. So now this is super simple. Yeah, let's just add those as comments like we did before. Okay, so x just this. Oh, we also need this binary prefix. So this is easy. Oh, return this dot x. Same here, and this should be return this dot pins, and we'll figure out pins in a moment. And this is just return 0, and all those reserved are also going to be we can probably put them together, just return 0 if it's reserved. ISR is this input shift reg, and there is also output shift register, so we'll define it in a moment. Output shift reg. So yeah, there is this input shift reg and output shift reg, and I think in reset we also need to remove them. So yeah, so in restart we said we are going to clear the input and output shift counters. The content of this dot input shift reg is 0, clearing it. And there is also input shift count, this is 0, and I guess this means we also have output shift count if we need to clear it. So let's define it. So input shift count and output shift count. So yeah, I guess these are like machine registers, state machine registers, X, Y, PC, those shift reg and shift reg count. Okay, so I think we finished with, oh, we still need to implement pins, but other than that, I think we, let's do together to do return 0. We have a bunch of to-dos here to finish, but yeah, but at least we are getting somewhere. Okay, so yeah, why, oh, arg, not args. So we have this source value, and now we just we need to do 2 things. First of all, we need to shift bit count bits from the source into this input shift register. So the direction of the shift depends on this register. So let's first of all figure out which direction should we shift. So if this dot shift control, and so if this is 1, then oh, that was the wrong one. We defined the out shift here, but there is the in shifter is the one that we need. So let's find it in the datasheet. Where is in shifter? That's 18. It's also the comment. So to the left, okay, and that was 18. Okay, now we can go back here, and if it's 1, then we said we are shifting. Go to out. We are shifting to the right. So we are going to this dot shift input shift register going to be shifted to the right by the amount of bits, bit count, right? And then we need to shift these new bits from the left, and I think we also need to reverse them. I guess that means we also need to reverse them, right? Yeah, that's the place where once we have the unit test, that would be super useful. This dot output shift reg, no, this dot input shift reg, this dot reverse, or just reverse bits of source value, and we need to shift them by 32 minus bit count. Or actually, we don't need to shift them because they are already we probably just need to mask them first of all. So we can probably mask the source value to make sure only the relevant bits are set. So I think this would probably create the correct bit mask, right? So if we have like let's see, if we have 5 in bit count, then that would be 1 shifted by 5 minus 1. Let's see how much this is in hexa, just to make sure we didn't mess up. So yeah, that's 1F, and that would give us just 5 bits. So that sounds good. Okay, why isn't it happy about something? Oh yeah, of course. And here we should just like this, it might be undefined, so just like reading, I mean it shouldn't, but let's just return 0 and have an error here to let us know something really bad happened. Source value with unsupported source, and then source, and then let's also do this for this jump condition with invalid condition. This is jump condition, and then it just returned false. In this case, it doesn't take the jump. Okay, and now we can probably go back here. So we still need reverse bits. We'll do it in a moment. Otherwise, if this is like shift, there is so if we shift it to the right, that enters from to the left. Otherwise, we shift it to the left, and that enters from the right. That's probably normally, I guess. So we just shift it to the left, and we just or equals to source value. And finally, once we got this figured out, we also need to where is that? Here, the in instruction. So in that case, we also need to Shift bound, shift direction, we did that. Increment the out input shift count by bit count, saturating at 32. So we should say the input shift count is plus equals bit count, and then if this dot is more than 32, then we should saturate it at 32. All right, and then oh, that's important. If we have a 0 here, we should just, shift all the bits. So basically, yeah. So if bit count is 0, that's a special case, then we just this dot input, we can probably break here, or else, I don't know, we may have some other logic later. So in this case, we are going to shift 32 bits, so it's just input shift reg equals source value, or depending on first bits, otherwise source value, and this dot input shift count is 32. Okay, we accounted for that. If automatic, will also push the ISR if push threshold is reached. In executes in one cycle, whether automatic push. So okay, state machine will stall if automatic push to all 0. Okay, so we also need to take care of this. Well, I will take a note that we need to do this automatic push. Okay, because we still haven't thought about how we do all those stalls and stuff. Always use the least significant bit count bits of the source count. Okay, that's good. Where's the ISR shifted to the left or right to make room for the new the data into the bit order of the input. Oh, that's important. The bit order of the input data is not dependent on the shift direction. So we don't need this manky reverse bits. We just need to make sure they are. So here we don't need this annoying thing. And here we just need to shift them by, yes, 32 minus bit count. So they are to the left. Yeah. The bit count can be 0 because we already handled this here. Okay, that simplified things a little. Null can be used. Okay, we have null. We don't have to worry about it. Okay, cool. So other than this to do with this automatic push, we already finished in. Let's take a look at out. What does out do? Probably quite the opposite. So it has destination and bit count, shift bit count of the out shift register, and yeah, it's very similar. So we probably need a way to write bits. So yeah, so let's do write destin out value, and there is destination value and how many bits we are going to write. And then let's do this scaffold of out. So yeah, we have this bit count, so it's, we still have to worry about this special case of 32 bits. We'll do it in a moment. So we have out, and there is like destination. So this dot write out value, and it takes const destination is just arg shifted by 5, so there is like destination, and we have this value. Where is it? From the OSR, this dot out shift reg, and we need to take only a few bits and then bit count. Yeah, and we also need to shift the out shift reg, so we'll do it in a moment. To do shift the right, or maybe we can do it now. Const value is, so I guess it also have like this thing with shift dir. This value oh, it says a 32 bits value is written to destination. It doesn't really matter, so we don't need to use bit count here. It's always like 32 bits value that we are writing. Okay, that's good to know. And then 32 lower bit counts come from the OSR. So and then I guess most or least significant bit. So if bit count is 0, then it's just like or maybe we can have a spatial case as well. If bit count is 0, then it just writes the entire shift register. It shifts all the bits, and I guess then there is also a counter. Yeah, it says something about counter, increase the output shift count. So this dot output shift count is 32, just the maximum. Else, so const value is, now it depends just like here on the out shift dir. Or maybe we can do else if the out shift dir is if the out shift dir is yeah, maybe we'll do it like we did, just copy this logic and then adjust it for writing. So we are looking at the out shift dir, and then there is like this const value is this dot output shift reg. So if it's true, then where did we have it? So is to the right. So if it's true, we are just taking the least significant bit. So it's basically we had this mask, so we can do the same trick here like we had here. Just take those bits, those lower bits, and this dot output shift reg is then shifted to the right, and then we have this dot right out value and destination with value. Otherwise it's the opposite direction, so we are just probably taking the lowest, the highest that's the highest bit, so 32 minus bit count. Yeah, so if it's 1 bit, it will shift 31. Yeah, we will have only 1 bit and the rest is 0. And then this is shifted, and then we can write this out value. And finally, we increment the output shift count, saturating at 32. Okay, so this is the out. We still need to implement write out value. But then yeah, we have pins and pins there. Okay, we'll get there. Yeah, we have this thing where yeah, where we need to take care of automatic pull, just like we have to take care of automatic push. So let's do this for now. And we have out exec allows instruction to be inline, the out itself, execute, and the instruction from the OSR. So there is a way to the state machine can sort of tell itself to execute another state machine. Okay. Delay cycles on the initial out are ignored, but execute may insert. Okay, this is like interesting. All right, so yeah, let's implement write out value, and then we just switch destination. And depending on the destination, we need to do things. So yeah, let's get rid of all of those things. And also, we don't need those two. Case 0b. And let's turn those into comments. Okay. Let's start with the easy one. So this.x equals x, equals value. This.y equals value. Discard data is super simple, just do nothing. And then here this.pc equals value, and we only want to take the lower 5 bits because otherwise it's not really valid. Okay. Okay, interesting. So in this case, we actually need a bit count because this.isr equals, does it shift those bits? I'm not sure. Like it says it's always 32-bit, right? So that's interesting. Let's try that. Just what it says. So we also need a bit count in this case, because in this specific case we need to write it. So this.input shift count is bit count, and exec, let's have this.exec equals value, and let's have a variable that holds this exec instruction. So that's an instruction we need to execute in the next clock cycle. And exec valid boolean. So by default it's false. It's actually not exactly a register, it's sort of state. So in this case, we are just writing that instruction to exec and setting exec value to true, break. Why it is not happy about this? Oh, it needs break here. And not happy about this because it needs break here. And this.set pins, and we can set the, this is actually set out pins because value. And this.set out pin dirs, pin directions value, and we'll implement those in a moment. Set out pin dirs, set out pins, right out pin dirs. Yeah, throwing is a good idea for now. Until we implement them, and this has to 32 bits and bit count and bit count. Okay, so cool. So we have most of the logic for out implemented. Yeah, we should probably have something that tells it to skip delay, because it says the delay cycles on the initial out are ignored. So let's have a skip delay that will be useful for this exec, or maybe we can also say so to do delay, but skip the delay if exec valid. So if there is an instruction to exec, then we need to skip the delay. And I think that after every instruction, we should usually update the PC, unless like this instruction is a jump. So I think we can probably have this variable update PC update PC, which is true by default, but then if we like had a jump, for instance, then we'll set it to false. So this dot update PC is true, but then in case of a jump we set it to false. And also if we updated PC here, then we don't want to update PC again. No, not here. Yeah, right. So in this case we don't want to update it again. And if we do want to update it, then if this.update PC, then this.pc equals this.pc plus 1. And then there is like this thing with wrapping, which we'll probably get to in a moment. So if PC reaches a certain value, we should reset it to wrap around. But for now, let's just make sure it never goes over the 32 bits limit. Cool. I'm not sure if the delay should come before we update PC or after. We'll see in a moment. Then we have push and pull, which are pretty simple, I guess. So there is like 2 flags for the push and 2 flags for pull, and they just copy data from the let's start with push because it's first. Pushes the content into the ISR into the RX FIFO. Clear the ISR to 0. So this dot RX FIFO dot push this dot input shift reg. This dot input shift reg clears to 0, and I guess it also removes. It doesn't say anything about the counter. Oh, there is don't do nothing unless the total shift input reaches its threshold. And there is also block, so we need to implement those. So that's in, I guess these are the same for push and pull. So yeah, E and block. So we can probably decode them at once. So let's say const block if this is true, like if arg and this bit is set, then, and let's boolean it, and this is like if full or if empty. So let's call it if full or empty depending on the instruction. That's this one. And then let's see, so if one can do nothing unless, okay, so we need to check this one. If full or empty, then we need to check, and this dot the count, shift count, input shift count is less than the threshold. This dot push threshold. Did I write it right? No, I'm missing an H. Threshold. Then break. We are not doing anything, and I guess it's the same for pull. Let's implement push threshold. It's just a simple getter. Yeah, we'll also have like get push threshold, and we'll probably have as well pull threshold as well. We are actually going to use them in I think in and out as well. Okay, so get push threshold returns shift control, this dot shift control, and let's see, where is this push threshold? So push threshold, that's bit 20, shift control, and or yeah, we probably need to we can just, that's like bits, we can shift it by 20 and then return those 4 bits, right? This is 4 bits, and then pull is like shifted. Oh, that's 5 bits. Okay, yeah, it's 32. So push, and I mean, it can be from 0 to 22, write 0 for the value of 32. So maybe we should const value is, then if there is a value, otherwise 32. And again here, the same thing, but a bit of a different logic. So that's shifted by 25, and that's the only difference, right? Yep. And then return those bits, and if it's value, otherwise 32. Okay, so we have those threshold. And now so if this input is less than the threshold, then just don't do anything, otherwise push. We still need to do this, I think, stall thing, right? Block. So let's just implement the logic for that. So if this.rxfifo.full to do stall. Okay, the assembler, if it's not, doesn't stall. Instead, continuing immediately. The next instruction, the FIFO state and the contents are unchanged. Okay. The ISR is still cleared, and this is flagging set. So if it's full, then there are two options. First of all, so if it's full, we either stall. If block, then we stall. Otherwise, we do we set this flag. So I think we had this flag somewhere here. Let's do it for now. To do set, and this will just clear. So if it's full, we'll just we are going to clear it anyway. But if it's not full, then we are going to push. So maybe it will make more sense. If it's not full, then push it. That's the happy path. Otherwise, if it's blocking, then stall. Otherwise, let the user know, and then we clear it. And I guess we should also clear the count. It makes sense to me, even though I don't see if it mentioned this explicitly, but it makes sure that it makes sense that if we like clear this queue, then we should probably set a count to 0. And there is also like this was push. Now we have, let's skip the push. Now we have pull to do, which is probably very similar to push. So yeah, load 32 into the OSR if empty, if nothing. Okay, so yeah, there is like if we're empty, but this one output shift count is pull threshold, then we do nothing. Right? For auto pull block, if txFIFO is empty. Interesting. If 0 copies pulling from an empty FIFO copies X to OSR. Interesting. Okay, so this .FIFO so in this way it's ds FIFO. Oh, wait a second. Sounding is strange here. This is ds FIFO. Wait, I'm confused for a moment. We are in pull, so we are pulling from txFIFO, and here inside push, it's the rxFIFO. Wait a second. Confused for a moment. Push the content into the rxFIFO. Okay, so this is if it's not empty. Yeah, I think something is wrong here. Pool is loading 32. Okay, cool. So now I'm fine again. So from the TX people, we are pulling. It's like the opposite into the this.out shift reg, right? So we are pulling 30 from TX FIFO into the OSR. If it's empty, then we probably need to set a flag. Install if it's empty, and if 0, pulling from an empty FIFO. Then if it's 0, then this.output shift reg, this.x. I guess it also clears the shift count, right? But for the output, okay. Should halt, should clock. This can be achieved. Non-blocking. Full on empty. The program can either reload the scratch register with the suitable default or move X after each recycled. Full if empty. An auto pull, when the OSR is full, so the pull is barrier. So we probably should to do that. So just if this is true, then we should just ignore this pull instruction. Okay, and I think I'm not sure we should probably once we like pull the value into the output shift register, set a count to 0. So yeah, so that's push and pull with a bunch of to-dos. We also have move, IRQ, and set, and I think we have just enough time to cover them if we don't do the test today, which is also making me a bit sad. So what I'm thinking, we may have another spontaneous session later this week where we will do the tests, where I'm also more focused. All right, so move has like source and destination, and it's probably again different. Or yeah, there is status. What is status? Ooh. Okay, interesting. So move is just copying values from source to destination. Let's go with set. I think it's a bit simpler. So it has destination and data. Write immediate value to data to destination, and it can write to pins. And I think there is like a different set of pins for set and different set of pins for out. Write to X, Y, and pin dears. Yeah, it seems pretty simple. This can be used. I think this is a simple one, unlike the previous ones that we had so far. So yeah, we have destination and data. So let's do this. This should be a piece of cake. So const destination is just, I think, the 5 highest bits, so arg5, and then const data is just yeah, we can probably copy from here the lower bits. Okay, and then if data, then do something. Oh, okay, so switch destination. There are just a very few cases here, so it might not be worth splitting it into a function. Break. So this dot pins dot there is like, I think there is already one for set set pins, because these are like a different set of pins, if I remember correctly, with data, or maybe we'll call it, how did they call it here? Data, yeah, data. And then there is like x, so this dot x equals data, so that's if we had 0, 0, 1. And same goes for this dot y, 0, 1, 0, right? And finally we have those pin dirs, which is 1, 0, 0, and the rest of the values are just reserved, so only 4 options. So that would be set pin dirs with data. And yeah, we got set, sort of, and we still need to do the IRQ and move, and I think we have one more missing. Wait, yeah, so all the things with we are still missing all the things with the clock and this stuff. Yeah, I think I will be careful, but I think we are more or less halfway through with the implementation here. We still have like a bunch of stuff we sort of to do, but at least it seems like we are starting to get at least the basics, the instruction set implemented. Already 600 lines of code, probably 600 bugs as well. A testing framework would be super useful here. Anyway, so let's try to do move. So in move we have like and this one will probably be best broken into 3 presets or 2 functions. Value is just this dot read move source, and source will have like the 3 lowest bits, so it's arg and 3 bits, and then we need to transform it according const, or maybe we can, yeah, transformed, or out value is this dot transform move value. It gets value and then it gets this op, which is const op is just, and we will just break it down to make it a bit more readable. So this is source, and then op is just arg shifted by 3 and 3, the lowest 2 bits. And finally this dot set move destination with destination and out value. All right, yeah, maybe out value transform value. Okay, and we also need to do destination, which is arg shifted by 5, take 3 bits, so that's the destination. Now we need to implement those 3 parts of this function, so let's do that. So read move source, transform, and set move destination. Okay, read move source. So source, depending on source, yeah, this is destination. Yeah, there are reserved values. Interesting. Okay, copy this. Yeah, so this is the source. So again, another switch. Let's get rid of all of those, and this as well, and then switch source and all those cases, and as usual make comments out of those. Yeah, okay, fine. Don't need all those spaces. I think that's great. And now yeah, return this dot pins, and I think this is the same pins as we had in, right? Yeah, in source and move source, really the same, like x, y, null, y, null. Yeah, there are like a few differences. So this dot x, this dot y, and this is like 0, and this is reserved. This is like also 0. I think it's actually the same as in, other than this status. So we can probably have these two together because it's reserved in anyway. So yeah, let's just double check it. Read in, or where is this in instruction? Execute in source value. So yeah, pins is 0, x is 1, y is 10, null is 11. These two ones are reserved, ISR, OSR. So yeah, so we can probably say this is reserved, and then here reserved for in, and status for move. Return this dot status, and yeah. Yeah, let's have get status to do, and there is like an explanation. Oh, need to do this. It's all either 0 or all ones, depending on this. Will probably 5 minutes to figure this out and implement this, but one more to do. Yeah, I think the next session will just be going over all those to do and getting rid of them. Cool. So we have we're missing in the space here, and then we can change the code to just in source value, and then let's do this transform value. So it gets a value and an up, and yeah, there are like 3 opcodes. So switch up. So if it's it just doesn't do anything, it returns the value as is. Case 0, 1, it bitwise complement. Yeah, this is a bit tricky. We need to implement bit reversing. So bit reverse value, and that's reserved. I guess it should just return the value as is reserved. Okay. Yeah, I think the easiest way would just be to Google for JavaScript. Stack Overflow should probably. That's the best way of programming. Yeah. Cool. But why do you need to convert it into a uint array? Yeah, that seems more legit without conversion. Bit reverse and x number. Yeah, I think I have seen this like trick to reverse the bits with those bit masks, which is probably quite cool. Anyways, so we figured this out. That's Stack Overflow oriented programming. My best. This should always. Let's just do it default. So, or just put both. So it's always returns a number. And now we just have to do this. Destination, like writing, and yeah, we also need to implement those declare method and declare method. Did just happen? I'm not sure. No, I don't want to fix. I want to declare this method. Okay, set pin dears, and we also What is not happy about it? Oh, this should be a number. And finally, we can, where is this move destination? Move. Let's see if it's the same as out, because this looks very familiar to me. So maybe we can just, there is like this function that we had that writes to out, write out value. Let's see. Pins, same as out. So that's 0, X is 1, Y is 10. This is reserved, or it discards the data. It doesn't really matter, I guess. Pin dears. Ooh, wait a second. Oh, it's not the same. Yeah, it's different, unfortunately. But we can probably copy at least the beginning. So I hope that would be the same, but it's not the case. So it's like this. Where was that? Set move destination. Yeah, so value. So yeah, that's pens x, y. This is served, and this is where things change. There is like exec, and we already have this logic here for exec, so just copy it here. And then PC is the same, and then this is ISR and OSR. Yeah. So let's see, how does it work? The input is reset to 0, and the output shift counter is reset to 0 as well here in OSR. And output shift reg equals value. Yeah, we can probably copy the comment here. Cool, ISR and OSR. Okay, and let's see if there are any interesting notes. Move PC, unconditional, out exec, move self, source the next, delay ignored, okay. Status and move can manipulate in limited ways. So yeah, invert twice, bit reverse. Okay, so I think we have move, which is pretty great. One more instruction, and yeah, I think this is a good opportunity to summarize and wrap up. So what did we have today? We had nearly more than 700 lines of PIO implementation. It's still not complete, but you see there is like, I think there are like probably 3 things or 4 things that in general we still need to do. Maybe I will write this down so we'll remember it for the next week. Yeah, a lot of warnings about all of those unused variables. Let's for now, no, I don't want to disable them. I want, but maybe it won't let me, no, it's only a warning. Yeah, let's see if it lets me commit or it complains. So maybe it, I hope it complains actually. It's a better behavior if it complains. Yeah, no, not tested, but fit RP2040. Implement start PIO implementation, or maybe work in progress, and that's issue number the issue number 61. Most of the instructions and registers are implemented. Still missing, so we are missing the part that connects the pins to the IO, or the IO pins to the state machines. So there are like all these set, where's that, set yeah, here, like set out pins and etc., but they are not implemented yet. So we are just, you know, we just need to implement those and read and write from the actual IO pins of the Pi Pico. And then we also interrupts and IRQs. We haven't implemented those. Wait, delay, clock cycle. I mean, everything that has to do with clock cycle. So waits, delays, etc. Waits until some condition happens. That's for in, for out, for pin jump. There is like, I think there was in jump, there was this like pin source that we haven't implemented yet. Where is the jump? In the jump condition, there is like this pin that we still need. Actually, we can do this because this dot out shift count more than 0. This probably means that the output shift register is not empty. So one less to do. Okay. Yeah, pin jump pin. So we need to do the waits, so stalls until some condition happens, e.g. FIFO is not full. And I think, oh, and we also need to do these debug registers, e.g. We had those like few debug registers that we said we would use them for dbg out, dbg OE. Just I think those will be super trivial to implement once we have like this one, like they connect once we connect the IO pins to the state machine, then it would just read those values, so it wouldn't be too hard. And interrupts and IRQs, clock cycles, wait. What about the instruction set? Let's see, we have oh, there is like auto push and pull. Yeah, so we are still missing IRQ. We did set, we did move. I think we are just missing instructions, IRQ and wait. And again, this like are related to these two interrupts and IRQs and wait. So once we do those instructions should be pretty straightforward. And I probably have missed a few spaces here that drives me crazy. Yeah, here as well. Yeah, some sort of developer OCD, I guess. So yeah, so we have I've surely missed something that we still haven't implemented, but I think that's in high level what we are still missing. Oh, and of course tests, lots of tests. But yeah, I think that's in a nutshell what we still need in order to get this beast to work. So maybe also in the clock divider, etc. Oh, and there is also this thing with the side set pins, which we only have this registers, but we still haven't implemented. So side set pins. Okay, so yeah, let's commit and push this very partial implementation. I really hope this commit will, no, it didn't. Yeah, so I should update the ESLint configuration so it doesn't like those values that are never read. But for now, that's it for today. So yeah, that's been a long, but I think it was a pretty fruitful session, and we have maybe a bit useful already. I mean, no, it's not useful yet, but it's close to being useful. PIO implementation. I'm probably going to have another spontaneous live session because we need this PIO to be working in after the next week for the last Raspberry Pi Pico deep dive course. So we have 1 more week to finish it. So I'm probably going to have at least some of the tests written in a spontaneous session. So I will keep you posted in the YouTube channel and the Discord chat. And until then, have a great rest of the week and see you again in the next session. Bye bye.